So let's start talking about the behavior of the system of conservation laws and how to solve them. So to analyze the behavior of the system of conservation laws, let's analyze them in one spatial dimensions first. So I'm going to write this as partial omega partial t plus partial f as a function of omega partial x equal to 0. So omega is now a vector. It's a system of conservation laws because I have many variables, but there is one spatial dimension only. Okay, so we can still look at the diagram of t and x. What's interesting is in the scalar world, we can derive the characteristics by differentiating this f, right? So in the scalar world, we can do this. We can take a wave speed out of this partial omega partial x equal to 0. Remember, we had u before, so this is df du. But in this case, we can also do that, but instead of getting a scalar, we get a vector. We get a matrix, df dw. So this is a matrix, right? So how do we get things like characteristics out of a matrix? Eigenvalues, eigenvectors, that's good. So let's look at the special case that this is a diagonal matrix. If partial f partial w is a diagonal matrix, what does that mean? That means it's just a collection of decoupled scalar equations, right? So that means if partial f partial w is a diagonal, that means each component of w only influences the corresponding f, the f that corresponds to the same equation that solves for that component of w. Okay, which means it's basically a collection of scalar conservation laws. Each variable doesn't affect the flux of other variables. And in this case, we can see for sure that we have multiple characteristics, each one corresponding to one of these scalar conservation laws. And what are the speed of these characteristics if this is a diagonal matrix? These are just the values on the diagonal, right? These are the wave speeds of each scalar conservation law. So if this is a 2x2 matrix, for example, and we have one positive and one negative diagonal entries, we have characteristics going in this direction, and also a set of characteristics going in that direction. They carry these two set of different variables in this way and that way. Now, what if partial f partial w in the general case is not a diagonal matrix? Then I think Xun said it right. We can perform eigenvalue eigenvector analysis. We can diagonalize this equation by pre-multiplying the system with a matrix U. So for example, let's say this is equal to U times lambda times U inverse. Okay, where lambda is a matrix containing all diagonals, is a diagonal matrix. Then what we can do is we can multiply U inverse on both sides of the matrix, both sides of the equation. So we have U inverse partial W partial T plus U inverse times this matrix, which is U lambda U inverse, okay, times partial W partial X is equal to 0. That's interesting because these cancel. And in the special case where the U doesn't depend on the solution omega, we basically have partial T of U inverse omega plus this diagonal matrix times partial U inverse omega partial X is equal to 0. And we can clearly see that we derive a system of conservation laws where each equation is decoupled. These variables are no longer the original W, they are U inverse times W. So if you do linear combinations of these variables in a particular way, then these linear combinations of the variables follow a conservation laws, follow their like individual conservation laws without interacting with the other linear combinations of these variables. And now lambda that contains the eigenvalues of the matrix corresponds to the direction of the and speed of these the system of conservation laws or the characteristics. Yeah. Mm-hmm. So yeah, I said if U does not depend on W, it's like a tool to, it's a special case where that gives us intuition on how this generally behaves. Okay. In general, the system of conservation laws doesn't behave simply like that. A system conservation laws behaves different from a scalar conservation laws exactly because this U can change with W. So what happens is that in a system of conservation laws, we no longer have straight characteristic lines. The characteristics would turn around because the U and also lambda changes as the solution evolves. So you can get cases where things are like that, things are like that. So you have characteristics converge and diverge from each other. They turn just like shockwaves do. And also a shockwave can appear out of nowhere and disappear. So it becomes very complex to analyze, and that's exactly why we need numerical methods. But these eigenvalues of the Jacobi matrix, I mean, this is called the Jacobi matrix of the flux. Okay, so a square matrix of how does the flux depend on the conserved variables. The Jacobi matrix, the eigenvalues, gives us the wave speed, which is very important in constructing the interface flux. Okay, if we know the wave speed from the left, we know the wave speed from the right. That tells me, okay, which direction the solution is coming from. It may come purely from one direction if all the characteristics are of positive sign, or all of them are from negative sign. Or different parts of the solution may come from different directions if some of the lambdas are positive, some of the lambdas are negative. Also, the magnitude tells me how fast the solution is going. So these are very useful information. That's why we look at the characteristics.